Okay, today we're going to look at acceleration and free fall. Free fall, by definition, is when an object travels up or down with only the force of gravity acting on it. So for example, if you were to take your pin and drop it to the table, when you release the pin, the moment you release it, it has a velocity of 0, and then it begins to accelerate downward to the ground. Same thing if you threw it up. It's going to have an initial velocity upward. It's then going to come to a stop at the top and then turn and accelerate as it reaches back to the ground. Again, that's what this discusses here, and that rate of acceleration is 9.80 meters per second squared. So again, what does that mean? It means that every second the object's speed will change by 9.80 meters per second. And again, we're neglecting air resistance in all these cases. That just makes it easier. If we have an HSE diver stepping off the high dive and striking the water 2.1 seconds below, determine the diver's speed at the time of impact. Well, let's look at our things that we know. What did we talk about when we dropped the pin? What is the initial velocity as soon as it's released from my hand? Well, it's the same thing when the diver steps off the high dive. The initial velocity is 0 meters per second. We know the acceleration is 9.80 meters per second squared, and we know the time is 2.1 seconds, and we're trying to determine the final velocity. So what equation do we have that relates these terms? That should come to mind. And then because V initial is 0, we're going to actually just cancel that out of the equation. And then we're going to solve for VF. So VF is equal to AT. Go ahead and substitute. And solve. And then to the correct number of digits, I have 3 digits on my acceleration and 2 digits on my time. So my answer is going to be rounded to 2 digits, which is 21 meters per second. Number 2 says determine the displacement of the diver. So now, you know, the diver's up on the high dive, up here. She's now stepped off and is falling down and hits the water. We want to know how far, displacement-wise, did that high diver fall when she struck, or he struck the surface of the water here. So now we're looking for D, and we know all of these things as well. And we calculate the final velocity. So you could do D equals 1/2 AT squared plus V naught T as an option. You could also use VF squared minus VO squared equals 2AD as an option. I'm going to go with the easiest one that I think. It's 1/2 AT squared plus V naught T. Because again, the initial velocity is 0, so 0 times t would then cancel or cross that out. So now I can substitute 1/2 times 9.80 meters per second squared times 2.1 seconds quantity squared. And I can do this all in one step. It's all multiplication and division. So again, 0.5 times 9.8 times 2.1 squared gives me a value of 21.6. Again, rounded to 2 digits, so I'm going to round that to 22 meters. Alright, try to see if you can do sample problem 3 on your own. Again, you can pause the video and then come back to it when you try that on your own. Okay, these are the givens and unknowns for the particular problem. Her shoe falls So therefore its initial velocity is 0 meters per second, and it strikes the ground at 80.1 meters per second. So that's where we get our final velocity there. Because it's in free fall, its acceleration is 9.80 meters per second squared, and we're trying to find the displacement. Again, pause again if you would like, and then work out the rest of the problem. So here's the problem solved. Again, using the equation VF squared minus VO squared equal 2AD. V initial is 0, so I can cross that out, leaving this equation here when solving for D. And then I substitute, and again it's all multiplication division rule, and solve to 3 digits. Again 3, 3, the number 2 has infinite, so my answer has 3. Let's move on. So now we're going to, those are objects that are falling. Now we're going to look at objects that are thrown upward. We're going to treat the upward direction as negative. That's critical. And the magnitude of the velocity does what? So if I throw the pin upward, what happens to its velocity, the magnitude of it? Does it get bigger or smaller? Well, it's going to slow down as it goes up into the air, so its magnitude is going to decrease. Upward velocity values are given a negative sign. Again, negative just tells us the direction, and downward velocities then would be given a positive sign. And if we're going to say up is negative, then any upward displacement is negative, and any downward displacement would also be positive then. So think of this, throwing up is a negative thing. Shooting up is a negative thing, and getting high is negative. So anything that's getting higher than what it was is negative. Anything that you shoot up into the air is negative. Anything that you throw up into the air is negative as well. It's a good thing to remember. So let's look at our example here. If we have an object that's thrown straight up, and there's the magnitude of the velocity, 29.4 meters per second. Zoom out here. The complete velocity with sign would be what? Well, it's thrown up, so therefore it is a negative 29.4 meters per second. What's it going to do? It's going to speed up or slow down when I throw something up into the air. Well, throw your pin up in the air that you're using, or your pencil. It slows down on the way up. So 1 second later, it's going to be 9.8 meters per second slower than what it was before. So again, the negative sign just tells me the direction. So if it's going to be slower, this magnitude, the 29.4, has to decrease. Or think of it this way. Acceleration is downward, so it is a positive value. So I'm going to take the negative 29.4, and I'm going to add 9.80 meters per second. So after 1 second, it's now traveling at a negative 19.6 meters per second. What's it going to do 2 seconds later from when it was thrown? Well, it's going to slow down another 9.8 meters per second during that next time interval. So now it's going to negative 9.8 meters per second. Again, another second later, it slows down again. So now at the top, this would be the top of its flight. It's now traveling at 0 meters per second, so it's stopped at the top. So if you throw an object up and you took a snapshot of what it's doing right at the top of its flight, it actually has a velocity of 0. Now what's it do? It starts accelerating downward, speeding up as it moves down. So 1 second after that, it's now traveling at, hopefully you're seeing the pattern, at 9.8. Another second after that, it's now at 19.6. And another second after that, it's now at 29.4 meters per second. So it's speeding up on the way down. So that magnitude continues to increase. So the magnitude decreases on the way up and then increases on the way back down. So it says here the object would return to your hand with the same magnitude of velocity as when it left your hand, but a different direction. Okay? Or a different sign. You could say a different sign would probably work in there. Recall that the slope of velocity versus time graph yields a value for the acceleration. So let's take a look at a velocity time graph for this. So here's what it looks like. I'll zoom in here so you can see. So we just plotted these points that we just discussed from before. So if you notice, when we threw it up with a negative 29.4 meter per second, and then the velocity continued to decrease in magnitude, and then it increased in magnitude as we went up. So if you notice, could we find the slope of that line? Sure, pick any 2 points on that line and we can find the slope. And if you notice, the slope is going to be positive 9.80 meters per second squared, which so happens to be our gravitational acceleration. It says even at the top of the object's path where the velocity is 0, the acceleration due to gravity is still that positive 9.80 meters per second squared. Therefore, we will always use the acceleration of gravity to be this. This is our gravitational acceleration for all of our problems. This just shows the slope of the line. It does a calculation for that slope. This is what that's showing there. Okay, let's look at the back side. Again, our next sample problem. We have a geyser in Yellowstone National Park is capable of shooting water from the ground with a speed of 48.0 meters per second. Determine the maximum upward displacement of the water. So again, pictures are always good. So if I have a geyser in the ground and the water is coming out, which direction is it moving? It's moving up. And what did we say with things that are being shot up or thrown up? They have what kind of velocities? Good, negatives. So that is a negative initial velocity. So when it says that it shoots out of the ground with a speed of 48 meters per second, that means the initial velocity is a negative 48.0 meters per second. We're trying to determine the height from here to here. So we're looking for the displacement. And if we know the velocity of water here at the bottom, what is the velocity of the water here at the top, at the final? Well, think about your pen or pencil that you threw up into the air. When we see it at the very top, we said the final velocity, or the velocity at the top there, would be 0 meters per second because it comes to a stop and then turns around and comes back down. And what do we know? It's accelerating at a rate of 9.80 meters per second squared. So those are our unknowns and our known values. I'll let you figure out the equation and solve. Pause the video and then come back. Okay, here's what we have. Here's our equation. VF squared minus VO squared equals 2AD based on the information we're given. V final is 0, so I can cross that out. And then I'm going to solve for D. So I get a negative V naught squared over 2A. I substitute my values in and I get an answer. Now most people would say, yeah, that looks good, it's 118 meters. However, this is incorrect. Can you see it? What is a negative squared? That is a positive. And you have a negative out front. So what should the displacement be? The displacement is actually negative 118 meters. Why is that? What does the negative sign tell us? It shows direction. In what direction is that water moving? It is up. It is higher than where it started, so it is a negative displacement. That is critical to get that negative sign right there. Okay, so for this last one, it's actually 3 problems in one. I'm going to kind of show you the setup and then give you the answers here. So the first one, the ball is thrown up at 39.2. Again, a negative for our initial velocity. And it wants to find the final velocity and displacement at 3 different times. So you actually have to do this 3 times. And the acceleration for all of the events is 9.8 meters per second squared. So pause the video. You might work out 1 or 2 of them in this space and then unpause the video to see the answer key. Okay, here are the answers for that problem. Again, the 2 equations that you're going to be using are the same for all 3 time intervals. And you can see the differences in the final velocities and in the displacements for the object.